Hi everyone. Let's talk about 3 ways of writing ionic equations. Okay, so it's a busy slide, but let's break it down. Okay, ionic equations. You know the ionic compounds. They're made of cations and anions. Some base positive and some base negative. Okay, it turns out that there are 3 ways of writing a balanced chemical equation. And here they are on the left-hand side. Well, let's just look at a specific example. First, if you read the top part, it says write the complete total ionic and net ionic equations for the reaction of, okay, what are we talking about? What specific molecules, what specific ionic compounds? Aqueous sodium carbonate with aqueous barium nitrate. Okay, and so there's an intermittent step here. I don't include it on my exams, but I guess there's a 4th way of writing a chemical equation. That's in a word form. And so what had to happen here is that someone had to, we just copy down the reagents given, and then you have to predict what the products are. Now, in a previous video, we talked about thinking about switching the cations to do that. It's called a double displacement reaction, where you actually swap 2 items from the reagents. We can look at that in a second as a review. And then after you convert the word formula to chemical formulas, you got your first method, your first way of writing ionic equations. And let's just list the formulas. That's what I have over here. Just kind of another way of looking at it. And this is the most familiar way that we usually write chemical equations. So sodium carbonate has a formula of 2 sodiums, Na2, CO3. Barium nitrate is Ba from the chemical, from the periodic table. Nitrate and carbonate are polyatomic ions. So we need to know those, that when we see the word nitrate, we think of NO3 with a -1. What's this 2 doing out here? Okay, so using the periodic table, you can go and look up barium. It's an alkaline earth metal. Remember, there's a video where we talked about families of elements. That means it's in column 2, which also means barium has 2 valence electrons. 2 electrons it wants to give away to become a +2 cation. So that's what's listed down here. Try not to get too far ahead of myself. We're still looking at the complete chemical equation, right? So when it says barium, look at the chemical equation, figure out that, hey, barium nitrate has this formula. Nature says then these pieces at cation and anion must group up so that they cancel out the charge. You have to balance out the charge. So it's going to take 2 nitrates and NO3 subscript 2 to balance out the barium. So there's the chemical formula for barium nitrate. And then let's swap the cations. So switch the barium, switch the sodium. Instead of sodium sticking the carbonate, let's have sodium stick the nitrate. And then same time, barium, leave nitrate behind and go stick to carbonate. And that's when you switch 2 items, 1 from each reagent, swapping those cations, that's a double displacement reaction. Okay, so sodium pairs up with nitrate, then you get sodium nitrate as one product. And when barium binds to carbonate, makes an ionic compound, you get barium carbonate. Cool. And that's a complete chemical equation, or sometimes called the full chemical equation. And it simply just lists all the molecules. Again, that's what you've been doing commonly in your chemistry classes so far. A balanced equation should also have physical states. So you're going to have to use the solubility rules to figure out that, hey, barium carbonate doesn't dissolve in water. Let's take a glimpse real quickly at the solubility rules, at least the way I teach them in my class. There they are there. You can pause the video, write them down, or take out a look at the other video where we talked about precipitation reactions. And that's actually what we have here too. So I called it a double displacement reaction where you swap in the cations. That's one way to classify the reaction. A second way is to realize that, hey, these were aqueous reagents. That's what the problem says up here. That's kind of nice. If you weren't told they're aqueous, use the solubility rules to figure out that sodium carbonate dissolves in water. Barium nitrate also dissolves in water. So they are aqueous, and these equations should have had a little aqueous here to be fully written correctly. Sodium nitrate is also soluble. Okay, one equation done. Why is there a second way? Well, as you look at these materials, these molecules here, yeah, the complete chemical equation kind of has everything, but sometimes you want to highlight the fact that in the water, in your aqueous solution, some of these cations and anions are not really stuck together. No, the dissolved ionic compounds means cations actually separate from anions, and water gets in between them. And so the total ionic equation expresses that. It realizes that sodium carbonate doesn't exist as all these atoms stuck together in waters swimming around. No, the sodium unsticks. You get +1 ions. I'm not a big fan of writing a 1 here next to the plus sign, but it's not incorrect. And there's 2 of them. And then the carbon anions, well, the C stays attached to the O's, right? How do you know that? Well, look on the periodic table to decide whether carbon, C, and oxygen, O, are metals or nonmetals. And you'll discover C and O are both okay in the upper right, where the nonmetals are. So we have a pair of nonmetals, and the pattern is nonmetals bond to nonmetals through covalent bonds. So no sharing electrons. Sorry, they are sharing electrons. That's covalent bonding. Ionic bonding is where one atom takes all the electrons away from the other. Ionic bonding. So this is covalent bonding. It's also a polyatomic ion. Another way to recognize, hey, the C and 3 O's stay stuck together as a net -2 ion, an anion. And that kind of swims around the water as an aqueous solution. And that's true for all the aqueous compounds, except for this solid, it's stuck together as a solid. And so in solution, no, barium and carbonate are all stuck together, and they're forming little particles, little crystals that you can see. It's a solid. You can actually filter this out. And that's a precipitation reaction. We take aqueous reagents and you make a solid or insoluble product. And then someone else might, a chemist would look at this and say, yeah, this is very illustrative of what a precipitation reaction is. Look, I see all these individual ions, and they all should be AQ down here to emphasize that they're all dissolved in water. And then what happened here? Why is this clumped together? Oh, it's a solid. Hey, that is a precipitation reaction. Nice. Okay, so usually we get the chemical equation first, and then if you need to convert it to the full ionic or total ionic, your choice of language here, you simply just change all your AQ formulas to ions. Be a lawyer here and say, well, under every circumstance, do you do that? No, only if it's possible. And to decide if it's possible, you use solubility rules and your knowledge of ionic and covalent bonding. So up here, NaNO3 was aqueous, and by solubility rules, salts that have sodium in them, that's the first solubility guideline, salts that have sodium in them are usually water soluble. Okay, and the AQ kind of confirms that, yeah, it dissolved. So separate your cations, 2 NAs, away from 2 NAs. Yes, 2 NAs, sorry, and 2 NOs, 3s, the nitrates. What about this part about the if possible? Well, let's look at a different reaction. Let's look at water dissolving table sugar, otherwise known as sucrose. And here's the equation for it. These little particles in here, the little crystals, they're sugar crystals. If you look in there, you'll find individual molecules. That one sugar molecule, the sucrose molecule, has 12 carbons, 22 hydrogens, and 11 oxygens, existing as a solid in dry form on the spoon here. And then once you stir it and give it some time, each individual molecule unsticks from the crystal lattice and swims around the water. This kind of diffuses about, and now it's aqueous. So a trick question would say, hey, write the net ionic equation to this. And you'll say, okay, where are my ions? Oh yeah, wait, if it's solid, leave it as a solid. But here's an AQ, so let's separate this into ions. But wait a minute, C's, H, O's, carbon, hydrogen, oxygen, they are all nonmetals. And nonmetals stick to nonmetals by covalent bonding. If it's covalently bonded, you don't have ionic compounds. We're done. That's a nice problem here. So it turns out there are no ions. So technically, you could say this is the net ionic equation. This is the total ionic equation, as well as the complete ionic equation. I'm sorry, the complete chemical equation. All right. So here, even though it's AQ, don't separate ions, or don't falsely separate ions, because there are none. It's all covalently bound together. Okay, the third way, and actually in some chemists' mind and other scientists, like doctors, the net ionic equation is the most important one. And so what's happening here? Well, go back to your total ionic equation and take a look at what's happening. You started with 2 sodium ions, and afterwards, you still have 2 sodium ions. You guys didn't change. You look at the carbonate ions, they were individually carbonate ions, aqueous, dissolved, swimming around about the water, and then afterwards, no, they're not swimming about, they're stuck to barium as a solid. Carbonate actually did something. Okay, so the most interesting part of this chemical equation, or the total ionic equation, is the fact that it is a precipitation reaction. We're making a solid. So why don't we just highlight that? Another way of viewing this is realizing that sodium, you did nothing. You're just watching the action. You're watching barium and carbonate find each other and precipitate out as a solid. You guys are spectator ions. You lazy bums, get out of there. So as a net ionic equation, in a net ionic equation, you cancel out, or just take them out, eliminate them, your spectator ions that do not change. And by do not changing, I mean the formulas are the same. Na plus is still Na plus, and the physical states are still the same. So these are both aqueous. That makes up a spectator ion. And you can take them out. So I kind of cut myself out here on the bottom. Let's get that in here. Yeah, spectator ions have the same formula and physical state on both sides of the equation. So if you look at carbonate, it's supposed to be a little AQ here, and afterwards carbonate's associated with an S. Okay, that changed. Don't cancel out. Barium, yeah, you were aqueous ions before, but now you're locked in a solid. That changed. Not a spectator. You're doing something. Nitrate, though, we had NO3 minus 1 and NO3 minus 1 afterwards. Formula's the same. What about the physical states? Well, it was aqueous before. It's still aqueous afterwards. They are spectator ions. Cancel them out. Don't pay too much attention to the coefficient when you're deciding whether something's a spectator ion or not. As you do more chemistry, you'll see more complicated reactions where, for example, in redox reactions, it's common that maybe there's 2 nitrates to start with, and then there's only 1 afterwards. One of the nitrates actually does something, but the second nitrate doesn't. So you still cancel out the nitrate, even though maybe the what's that called? The coefficient, there's 2 in front. Maybe that changes. Just ignore that part. That's okay that that changes. If you have NO3 minus aqueous and NO3 minus aqueous afterwards, then eliminate the ones that are not changing. We'll talk about that more if we see complicated redox reactions. Okay, what's the net outcome? What's the net ionic equation? You're canceling out the nitrates, cancel out the sodiums from both sides, and then you're left with barium, and just out of matter of preference, they decide to list the cation first. You don't have to. but oftentimes we do. And then the carbonate second, and then the product. And if you had balanced your equations correctly, this should automatically be balanced. But as a good check, make sure, right? So there's one barium on the left, one barium on the right, one C, 3 O's, yeah, it's still balanced good. And health professionals, scientists love this because it gets right to the crux of the matter. What's important here? It's when barium ions find carbonate ions, it precipitates out. And so some diseases, medical conditions like gout, kidney stones, gallstones, what's some others in there? Anyways, these are compounds that are precipitating out body fluids, or, you know, in the kidneys, I guess it'd be precursor of the urine, and causing problems. So what's happening there? Well, what's the molecule that's actually precipitating out? And what are the ions that are producing that insoluble compound? And that Net Ionic Equation just gets right to the heart of the matter. Cool. All right, so gone over what makes up these three types of reactions. We've hit the highlights, right? How do you tell them apart? How do you convert one to another? First one, full chemical equation, has just the chemical formulas. The full ionic is where you convert all your aqueous formulas to ions. Yeah, if possible, if they truly are ionic. And then finally, Net Ionic Equations cancel out your Spectator ions. And we can recognize Spectator ions by those species, cations, anions, that are the same, they have the same formula, and the same physical state on both sides of the equation. Cool. Let's do another one. So suppose on your next exam, which is quite likely, you might see something like this, a sample exam problem. Write the complete chemical equation, the total ionic equation, and the net ionic equation for the reaction between ammonium phosphate and mercury 1 nitrate. Okay, this is a loaded question. First, you want to write the complete chemical equation, which means we're going to write out the chemical formulas. So you got to know your polyatomic ions. What's ammonium? Well, the ammonium ion is NH4+. What's phosphate? Well, it starts with a P. Phosphate, that's a good example, or a good clue. And then you have to know there's 4 oxygens with a net -3 charge. Okay, so the compound ammonium phosphate exists when these cations and anions group up to cancel out the charge. And right now we have a +1 trying to cancel out a -3. That doesn't work. So if it doesn't cancel out, a little shortcut is to do the crisscross method. Take this 3, put it down here. Take this 1, put it over there. And the formula for ammonium nitrate is where you have 3 ammonium ions. So together it's a +3 charge and 1 phosphate. Cool, that's the chemical formula. And then mercury 1, well, if you go to the periodic table, mercury is Hg, has a +1 charge. So you might be thinking, oh, there's my formula. And like, oops, sorry, that's not correct. The mercury 1 is one of those weird polyatomic ions. The actual formula for mercury 1 is 2 mercury atoms bond together. Each one is a +1 charge, but together they sum up to +2. Nitrate, we saw in the previous example of above, that's NO3 with a -1. And then nature says group up to balance the charge. We're going to need 2 nitrates. So together we get a -2 charge. Oh, parentheses, please. There we go. So there's the formula for mercury nitrate. Next, we got to predict the products. I know, it's a process. Okay, but what we're going to do is follow the switch the cations idea. We're going to assume it's a double displacement reaction. And hey, ammonium ions, you switch places with the mercury 1 ions, which means mercury, you're going to be stuck to the phosphates now. And let's go back to the original ionic forms. And ammonium, you stick to the nitrates. And some of you are saying, wait, there's 3 ammoniums. Aren't you supposed to bring all 3 over? Okay, that is trying to balance the equation. Right now, we just want to get the correct chemical formulas, right? And nature says, no, it doesn't matter how many ammonium ions you have and how many nitrates. In your product, you have to balance the charges. And so what I do is, let's save balancing for later. Ignore the fact that, yeah, you do start with 3 ammoniums, but let's just get the formula for the product and deal with the 3 later. Okay, so what do? We switch the cations, and now mercury is trying to stick the phosphate, but the 2 and the 3 don't match. So do the crisscross method. Take phosphates 3 and say, hey, mercury, we're going to give you 3 of those. Ooh, what a weird formula. And phosphate, you got 2 of those. So I did this on purpose. I don't expect you to see such a crazy looking molecule on your exams, but if you do, you're ready. That's all you do. That's chemical formula. Because in here, if you write it out, it says you have 2 mercuries. Each one's a +2. Sorry, that's a 3. There's 3 mercuries, polyatomic ions. And then there's a 2 out here. It says you have 2 phosphates. And so the compound that is mercury 1 phosphate looks like this, but we write it like this, right? Because the mercuries all add up to a total of 6 pluses. Phosphates add up to 6 minuses. Hey, that balances the charge. Nature likes that. That makes for a stable molecule. Ammonium nitrate. Hey, this is nice. The +1, -1, they already match. The formula for ammonium nitrate is simply NH4NO3. No parentheses needed. Just smash all those letters and numbers together. Cool. Okay, so now we predicted products. We're still after the complete chemical equation. Let's write out the reagents. Well, we begin with ammonium 3 phosphate. Right, so ammonium phosphate, it's 1 reagent. We add in the mercury nitrate. I don't know what this is doing. Move that out of the way so you can see the question up above, see our work. Mercury 2 nitrate with 2 of those. And they're going to change the cations into mercury phosphate and ammonium nitrate. Good. We're not done. We have to have a balanced chemical equation. So the complete chemical equation, they must be balanced. So my guidelines are, don't change the subscripts, right? So I know all these crazy numbers outside parentheses are there. You gotta leave those alone. We took some time to figure out what the subscripts were. That was to get the balance, get the charges balanced. Okay, so don't change those. Second guideline, save the simplest molecule for last. And right here, there's only 1 molecule that doesn't have any parentheses, and that's the last one, the ammonium nitrate. So save that for last. Don't balance that yet, which means don't balance nitrogen, don't balance hydrogen, don't balance oxygen. Go after another element. Well, that leaves mercury or phosphate. Sorry, phosphorus. P or Hg. Yeah, doesn't matter which one. Let's try Hg. Okay, so 2 times 3 is 6. So on the right side, there's 6 mercury atoms. What about the left? There's only 2. So you have to put a big 3 here, so you have 6 mercuries. Matching 6 mercuries. Nice. Let's do phosphorus, P. Right now, there's 2 phosphorus. None over there, good. There's 2 phosphorus on the entire right-hand side. How many are on the left-hand side? Oh, just 1. So put a 2 here. Okay. Well, we're done, balance all the atoms that are not in the simplest formula. So now save the simplest for last. We're there. You can pick nitrogen, hydrogen, or oxygen. Let's just pick nitrogen. So what have we got? Ooh, lots of math. The N is inside parentheses, so there's 3 of them. And then we multiply by 2. There's 6 N's here. How many are here? Huh, same deal, really. There's an N inside parentheses. There's 2, and a big 3 out front. There's also 6 N's. There's a total of 12 nitrogens here. On the right-hand side, there's no nitrogens in mercury 1-phosphate, but there's 2 of them in ammonium nitrate. I need to get 12, not 2. 2 times 6, though, is 12. Nice. Okay, nitrogens are balanced. Go after hydrogen or oxygen, doesn't matter which. I'm going to pick hydrogen. So it's 4 times 6 is 24 hydrogens. Yikes. On the left-hand side, no H's here. How many you got here? 4 times 3 is 12. Ooh, times 2 is 24. Phew, hydrogen is already balanced. 24 on each side. All right, oxygen. You're all over the place. Everybody's got oxygen. How many we got on the right side? We got 4 sorry. There's a 4 on phosphate. Times 2 is 8. So we have 8 oxygens here. And then we have 3 here. Times 6. That's 18 oxygens. That's 26 total on the right-hand side. We better have 26 over here. So what we got? We got a 4 here. No parentheses. Nice. Times 2. Okay, so there's 8 oxygens here. What about this one? It's 2 times 3 is 6. 6 times 3 is 8. 18 again. That looks familiar. 8 and 18 is 26. And 8 and 18 is still 26. Yes. Yeah, what a horrendous problem, but it's balanced. We're done now, right? No. Okay, the hardest part's over. We just need the physical states. Okay, so from the problem, we're not told these are aqueous or solid or whatever. We're going to assume that water is involved here. Maybe it should have said for the reaction in water, so that you realize there's a chance things could dissolve because there is some water. And then we have to use solubility rules. Okay, so we got ammonium phosphate, mercury nitrate. Let's start with those two. Take a peek at the solubility rules, which we're supposed to have memorized. The ammonium ion, NH4, usually means things are soluble. And nitrate usually means things are soluble. So let's just verify that. Yep. So the first guideline is salts of the ammonium ion. There it is, NH4 are soluble. And then down here, salts of nitrate ion, NO3, minus 1, soluble. What else do we got? Put it on the screen. Okay, so first compound is ammonium phosphate. That has ammonium ion in it. That should be soluble, AQ. Nitrate's here, so the mercury 1 nitrate should also be soluble. And what about the mercury phosphate? Well, go to the solubility rules, and mercury, when it's attached to either sulfate or the halides, chlorine, bromine, iodide, doesn't dissolve. What about phosphate? Phosphate's not on the solubility rules at all. And our 5th guideline, the solubility rules, is if the ionic compound is not listed, assume it does not dissolve. And that's actually a good prediction. Mercury 1 phosphate is not water soluble. It forms a solid. What about ammonium nitrate? Oh wait, ammonium, there it is, it's soluble. Nitrate, wait, that's also predicted to be soluble, and yes. Ammonium nitrate is soluble, and yes, we finished the first of the chemical equations. We have the complete chemical equation here. But there's 3. Yeah, so if this problem shows up on your exam, it's loaded with points. Show your work. And so if you make a mistake, you can at least get some partial credit. So we'll rewrite this a little more neatly. We have 2 of the ammonium phosphates that are aqueous. React with 3 mercury 1 nitrates, also aqueous. Going to a solid. Hey, this is a precipitation reaction. Mercury and phosphate is the chemical formula of the solid or the precipitate. And then the byproduct is 6 molecules of ammonium nitrate that are dissolved in the water. Complete ionic equation. Next one, oh, maybe I should write that. Let's put it up here. This is the complete chemical equation. Let's go after the full or complete ionic. So what you do is just change AQ to ions. That's the guideline. So that means leave this compound alone. It's not an aqueous compound. So in your full ionic equation, complete ionic equation, goes by a couple different names. The mercury 1 phosphate, excuse me. What's solid? It stays solid. But, excuse me, the ammonium phosphate was aqueous. We can go and look at our work. That's a good idea for showing your work. And we realize, hey, ammonium, where are you? Go farther up. There you go. The ammonium ion is NH4 plus. Phosphate is PO4 minus. So when we're converting our complete chemical equation to full ionic, just write NH4, and it's aqueous. But then how many cations come off of this molecule? Well, in one simplest molecule, there's 3 ammoniums. But to balance it, you need 2 of the ammonium phosphate. So there's 3 times 2, there's 6 ammonium ions here. 2 times 3. How many phosphates? Well, in the molecule itself, there's just 1 phosphate, but you have 2 of these molecules. So there's 2 phosphates. Cool, we just converted the first molecule into the set of ions. What do we have here? We have mercury nitrate. It's aqueous, so start separating cations from anions. Mercury, it's one of those polyatomic, so there's 2 mercury atoms together making a +2 charge, aqueous. And it's a total of 3. I'll squeeze it in right there. Nitrate, there's 2 of the nitrates, but 3 of the molecules, that's 6 again. Cool. And then over here, we left the solid alone. So go after the other aqueous. There's 6 ammoniums. There's a plus with an AQ, and I'm running out of room. So I'll put it down here. There's also 6 nitrates. Awesome. That didn't take too long. And it was helpful that we could go back and look at our work of doing the complete ionic equation to get the formulas for these cations and anions. Okay, last thing to do is net ionic. And the key is cancel out the spectators. Who's not doing anything? Who's just along for the ride? Spectator ions. Okay, so just inspect them one at a time. We have NH4 plus aqueous on the left and NH4 aqueous on the right. So a little slash to that to remind you, don't copy that. It doesn't exist in the net ionic equation. Phosphates, you guys doing anything? PO4 minus was aqueous. Ooh, but afterwards it's solid. Yes, you guys stay, you did something, you changed. Mercury 2 plus, aqueous. Hey, you guys stick around too, you're in the solid. You changed. But these 6 nitrates, you guys did nothing. You're just watching mercury and phosphate form solids. Cancel those out. And then we simply have, and again, your choice. Do you want to list the anion first? I'll give you full credit. Most people are going to put the cation first. So to make your answer look like the answer key, and you don't have to, but we generally put the cation first and then the anion second. Keep the subscripts, I'm sorry, these are coefficients. Keep subscripts too, but keep the coefficients, the 2 and the 3. That's aqueous, and it's a -3 charge. And it's forming a precipitate, and there's the formula for the precipitate. And now we have the net ionic equation. Cool. Let me show you one shortcut. Scroll up a little bit here. Well, let's move this. If you are not asked to write the full ionic, you can take a shortcut. You'll probably have the complete ionic equation, and you can look for precipitation reactions and say, okay, I got two aqueous reagents forming a solid, and the byproduct is not a solid. That's kind of rare, but it can happen. Can it? Maybe not. Don't think so. Sorry, distraction. If you look here, you saw start with two aqueous reagents and they make a solid. That is a precipitation reaction. Precipitation, what's that mean? You made a solid. So grab the equation, the formula for the solid, and break it up into ions. And that's a nice shortcut. So if you recognize this is precipitation, Mercury 1 phosphate has this formula. And within that formula, hey, there's 3 mercury atoms, so 3 mercury ions, I should say. And then in this formula, there are 2 phosphates. So yeah, so 2 phosphates, and boom, you got the net ionic equation right away. Okay, that's enough for now. Take care.